Hello my friends, welcome to Docinnet channel. Follow today's video. Today's video is about quality of service. Okay, let's go. Quality of service. In a standard IP network, all packets are processed identically based on best effort. The network devices usually ignore the importance or criticality of the data that is passing through the network. This creates problems in deployments where time-sensitive traffic, such as voice and video packets, is delayed or dropped because the network devices do not prioritize it over other traffic. The feature of prioritizing some traffic over other traffic is known as quality of service. Imagine a long-distance phone call that involved a satellite connection. If the conversation is interrupted with brief but perceptible gaps at odd intervals, you cannot tolerate long latency times. Using quality of service, you can prioritize the VoIP traffic to prevent against bandwidth hogging and protect time-sensitive traffic. Quality of service is useful in almost any network deployment, including the following. You run voice, video and data traffic on the same network. Because voice and video streams are time sensitive and do not tolerate network delays, quality of service policies must be implemented to ensure traffic prioritization. You run data applications such as time sensitive database that require traffic prioritization if there is congestion on the network. You want to prioritize management traffic such as telnet or SSH so that you do not lose access to the network devices if there is an outbreak of a new virus in the local network. You are a service provider and want to offer different classes of service to your customers based on their needs. You have virtual private networks VPN deployed and you want to prioritize or rate limit traffic going over the VPN tunnel. Quality of service is useful in policing, shaping and prioritizing packets only when there is congestion in the network. For end-to-end quality of service, all network devices along path should be quality of service capable. Many different types of quality of service mechanisms are available in the Cisco devices such as the following. Number 1. Traffic policing. Number 2. Traffic prioritization. Number 3. Traffic shaping. Number 4. Traffic marking. Quality of service types. Cisco ASA supports 3 types of quality of service: traffic prioritization, traffic policing, and traffic shaping. You configure all these methods by using the robust modular policy framework. Traffic prioritization. Traffic prioritization, also known as class of service or low latency queue, is used to give important network traffic precedence over normal or unimportant network traffic. It assigns to traffic different priority levels or classes such as high, medium, and low. The lower the packet's importance, the lower its priority and thus the greater its chances of getting dropped in case of network congestion. In the current implementation of Cisco ASA, 2 classes of traffic prioritization are supported: priority quality of service and non-priority quality of service. With priority, quality of service packets are prioritized over regular traffic, whereas with non-priority, quality of service packets are processed by the rate limiter. When traffic is classified as priority, it gets expressed forwarded without passing through the rate limiter. The traffic is then flagged to take the priority queue at the egress interface level. Traffic policing. Traffic policing, also known as traffic rate limit, allows you to control the maximum rate of traffic eligible to pass through an interface. Traffic that falls within the configured parameters is allowed to pass, whereas the traffic that exceeds the limit is dropped. Traffic shaping. Traffic shaping is a mechanism that enables you to control the rate of traffic through the security appliance. This is extremely useful in scenarios where you have congested WAN links and you are sending more traffic through the security appliance than your WAN link can support. For example, if you have a 5510 with a 100 megabit per second interface with an upstream internet gateway with a 10 megabit per second uplink, then you can define traffic shaping policies on the security appliance so that the excessive packets can be queued up for transmission over time at the configured rate. If the queue is full, packets are tail dropped. Traffic shaping is implemented when a packet is about to be transmitted on an outbound interface. This includes shaping both through the box and from the box traffic. With traffic shaping, you cannot shape traffic in any traffic selection class other than the default class. Shape traffic on multiple VLAN interface defined under a physical interface. Packet flow sequence. When a packet passes through a security appliance configured for quality of service, the following sequence of events occurs. Step 1. The packet arrives at the ingress interface. If it is the first packet of the flow, the security appliance attempts to route the packet out to the proper interface and creates a flow for the subsequent packets. The flow contains the role and actions associated with the packets. Step 2. Based on the quality of service roles, the security appliance takes one of the following actions. Number 1. If the packet matches priority queue, it is directed to the prioritized queue for express handling. For the priority queue, there is no rate limiting on the packets. Number 2. If rate limiting is configured on the security appliance, the packet is checked to see whether a flow for quality of service is already established. If there is a none, a flow is created based on the source and destination IP address, source and destination ports, IP protocol, and the interface forwarding the packets. The security appliance checks that it conforms to the configured rate limiting parameters. If traffic matches a rate limiting policy but exceeds the threshold, the security appliance drops the packet. If traffic does not match a rate limiting policy and a default class is defined with traffic shaping, the security appliance shapes traffic based on the configured parameters and buffer burst traffic in the queue. Step 3. At this point, the quality of service flow is up and the packet is forwarded to the egress interface for physical transmission. Step 4. The egress interface has to allocate queues for quality of service. One is used for the prioritized traffic and the other is used for the non-prioritized traffic. If traffic is rate limiting and there are packets to be sent in the prioritized queue, the security appliance services the prioritized queue first and then processes the rate limited queue. Step 5. The security appliance transmits the packet over the physical interface. Packet classification. Packet classification is a way to identify packets on which quality of service policies need to be applied. This can range from simple functions such as IP precedence and DSCP fields to complicated methods such as complex access lists. IP precedence field. IP packets contain a type of service byte which is used to indicate the priority in which the packets should be processed. In the TOS byte, the leftmost 3 bits set the IP precedence as shown in figure. The network devices use the next 4 bits, known as the TOS bits, to determine how a packet should be handled by looking at delay, throughput, reliability, and cost. IP DSCP field differentiated services code point is to replace the definitions of the IP TOS byte. DSCP field takes the same space within the IP header as the IP TOS byte. It uses the 6 most significant bits for packet classification. The 2 least significant bits are currently unused, as shown in figure. By using the 6 bits in DSCP, you can classify up to 64 streams of packets. Okay, today's video is finished. Please send our videos to your friends and be sure to like and subscribe.